All right. So today I would like to continue in finite elements, and we'll talk mainly about finite element discretization of elastic potentials. But first, let me start with what we ended the last time. So previously on phys-based, we talked about how to discretize the kinetic energy using finite elements, and that led us to the mass matrix, right? So kinetic energy, just to remind you, in the continuous world is the integral over your domain omega, and it's the density times the square of your velocity integrated over the entire domain. And what we did the last time is we created a finite element approximation. That's what I kind of mean by this double tilde, like almost equal. And that boiled out to VTMV, where the V, that means that's like a 3n dimensional vector, right? Sorry, I meant R3n. Whereas the usual thing that it stacks the V1 to Vn. And what does that mean? That means that I have my domain omega. Let's see that this is a subset of R2. Let me write it in R2 to be clear. It also works in R3 with that, but it's almost the same thing. Well, and then these VIs, those are velocities at my nodes. So there is some tet mesh living in your domain. That's how you discretize the domain. That's the kind of the key idea of finite elements. There are some big nodes, and there are some edges forming triangles. And so each of the nodes has a sample of velocities, so v1, v2, v3, and so on. And all of them go into this vector. And this VTMV, that's the finite element approximation of the kinetic energy. The M, of course, is a 3n by 3n matrix. We said it's symmetric and positive definite usually, at least positive semi-definite. Maybe let me show you that actually computing the mass matrix the way we defined it last time. So we said that we're going to assume that the density is constant on every single triangle, and then the velocities are interpolated inside the domain using piecewise linear shape functions. Okay. Under these assumptions, computing the mass matrix is actually quite easy. Let me write it in terms of like pseudocode to kind of make the point that it actually is really easy. I was explaining the last time, but I didn't really like show the algorithm, so let me make it very clear. So for every triangle, so you do loop over all triangles, and then you do a loop for every triangle. You go over all its nodes. So for all nodes I in T, and what you do, you're gonna take the diagonal part of the mass matrix, and you're gonna add there, like accumulate the density times the area of that specific triangle divided by 6. Okay. And then we also have a loop over edges. So for all edges, so ij in the triangle, what we would do, we would add to mij, we would add a similar thing, except that would be divided by 12 this time around. And that is it, okay? That's how you compute the accurate mass matrix that discretizes this energy under the assumption that these rhos are constant on every single element and that the velocities are linearly interpolated inside the domain. Okay? Just to remind you, the linear interpolation of the velocity, that meant that we actually write the approximate like this, approximate using a sum over all of the nodes, so from 1 to n, of the samples of velocities, the VIs, times the shape functions. Okay? Do you remember how the shape functions look like? Let me bring up the image, which I had somewhere. See if I still have it here. That's how the shape functions look like. Okay, this was our SI. This thing is SI for where I is this vertex over here. Okay, all the remaining vertices have 0 there. Those are the piecewise linear shape functions, sometimes also known as head or tent functions, because that's how they look like. And I also said that often people kind of approximate this mass matrix with a lumped mass matrix. And the idea of lumping basically is that the off-diagonal elements, you lump them onto the diagonal. Okay, so because the rho t at, that's by the way, that's the mass of triangle number t. Okay, so this denominator, the thing, the thing on top, that's the numerator, yeah. The numerator is the same in both, okay? So if I sum these things, if I sum 1/6 plus 1/12 plus another 1/12, right? Because every vertex, every eye will have two edges, two j's. So on every row of the matrix, you will have 1/6 and 1/12, okay? So if you sum it, that's of course 1/6 plus 2/12, meaning 1/6, which means this is 2/6, aka 1/3. Okay. So instead of putting these off-diagonal elements, what the lumping basically means is this. Okay, you get rid of this and you replace this with 3. Oh, and by the way, there is this little detail that this II actually means the entire 3x3 block, okay? Because this is just a technicality, because these things are not scalars, but 3x3 identity matrices scaled by this number. Okay, that's so this makes sense. All right, so oh yeah, and that's why I'm repeating all this, because the last time I asked you a question, what is the finite element interpretation of the mass lumping, right? Is it just like some weird hack that like some people did and find out that it works by coincidence, or is there some justification for it? The latter is the case. Did anybody think about that? It's actually kind of cool. So let me explain you the finite element interpretation of mass lumping. It's actually, once you get this, then you kind of can say that you understood the idea of finite elements. So here, and that's by the way the standard setup. You assume that you have your velocity sampled at the nodes, like shown here, and then you linearly interpolate inside the domain. Okay, and that's exactly this formula. As I told you before, you have a lot of flexibility in choosing the shape functions. Okay, the shape functions, they don't have to be these head functions. They need to be interpolating. They need to sum to 1. They better be local if you want to be performant. They definitely don't have to be piecewise linear. So what is easier to do than piecewise linear? And we kind of did it for the triangles, right? If you remember from the last time, I said, hey, the densities are going to be constant on every triangle, so meaning piecewise constant shape functions, meaning one, like for example, shape function for this triangle would be 1 here on this entire area of the triangle, okay, and would be 0 everywhere else, okay? So can we do the same trick for the velocities? Can we make it simpler, basically? Can we, instead of these piecewise linear shape functions, can we use piecewise constant shape functions? And the answer is yes, and if you do it right, you will get exactly the lumped mass matrix. Now there is a trick, however, right? And let me you can kind of see it from here, right? Like, I still need some way of interpolating the velocities inside all of this continuous domain, right? I can bring up, at any point, I need to be able to say what is the velocity there. That's what the shape functions do, right? They interpolate the sampled velocities, and they tell me for every point, that's this point, this p, so for every point p, I need to be able to tell what is the interpolated velocity. So I cannot really do it the same way as before, right? It would be kind of weird to say that the velocity now lives on the triangles, because I guess it would be theoretically possible, but then you would have like a discontinuous velocity field, which would not be bad per se. But the problem is that then you have also positions for all the nodes, right? And the positions also naturally live on the nodes. So here is how you can do this, and it's actually kind of cool geometric thing. If you take an arbitrary triangle, let me try to draw a better triangle like this. So this is the triangle. That's kind of the basic building block of all these finite elements. You can compute a thing called the barycenter of the triangle. Okay, so if these vertices are called A, B, and C, the barycenter is simply 1/3 of A plus 1/3 of B plus 1/3 of C. Okay, it's also the center of mass of the triangle, by the way. And the interesting thing is that if you take the barycenter and you connect it to edge midpoints, so you can divide each of the edges in half. Okay, you can do this. And if you connect it like this, connect the barycenter to all of the edge midpoints, what's going to happen is that you split the triangle into 3 equal areas. Okay, so the area of this piece will be the same as the area of this piece, and that will be the same as the area of this piece. Okay, and that's because we pick this to be the barycenter, and those are the edge midpoints. Okay, so if we have a mesh like this one, but maybe let me write it, let me draw it a little bit nicer. So if I have some general mesh, by the way, it doesn't have to be convex. Okay, the neighborhood of a single vertex, it could easily look something like this. Let me exaggerate it a little bit. Was not that non-convex, but you got the idea. Okay. So let's say this is the vertex I'm looking at, and it has these adjacent triangles to it. Well, I can do this barycentric division on all of them. Okay, so I can look at the barycenter of all the triangles, and I can find the edge midpoints for all the edges, and then I can just connect this. Okay, or maybe with a different color to make it more clear, and I can connect this with lines.
So you see barycenter like B-A-R-Y.
Yep. Sorry.
Okay. What sort of center did you call it?
Let me write it down. This is the barycenter.
Okay.
You have probably. Oh, am I just pronouncing it wrong?
No, I don't.
You have certainly heard about barycentric coordinates, right? No. So that, by the way, the 1/3, 1/3, 1/3, those would be barycentric coordinates of the barycenter. Okay, barycentric coordinates is something very simple. That just means that every point inside a triangle you can write as a linear combination, actually as a convex combination of A, B, and C. And they are just weights between 0 and 1. That's how it's also like usually interpolation done in graphics. If you're interpolating from vertices inside a triangle using barycentric coordinates, you can just look it up on Wikipedia. It's pretty simple.
Yeah, that's part of the reason why I want to know how to spell it.
Yes. Okay, like this. Yeah. I'm not sure where the word came from, but I'm sure you can. Which, by the way, the thing I just drew here, so I took the barycenters, connected them with the edge midpoints. This thing is called, if I'm already writing the spelling stuff, this is sometimes called barycentric cell. Okay, so the idea is that you have this one node, and this node has some velocity with it. Okay, and I constructed this barycentric cell so that I can now define very special shape functions, piecewise constant shape functions, and the shape functions, let me call them like SI with tilde or something. So the SI tilde of P will be either 0 or 1, okay, and it will be 0 if P is outside of the barycentric cell. Let me call this BC, and it's 1 if it's inside. Okay, so what that means is I can define a shape function such that the shape function is 1 everywhere inside this barycentric cell. Okay, it does not have to be convex, and is 0 everywhere, and is 0 everywhere else. Okay, and that's a shape function corresponding, if this is vertex number I, that's a shape function corresponding to this node. Okay, so that's you can kind of if you compare it to these head functions, it's kind of like a one order lower approximation or one order less interpolation, right? This interpolation with the piecewise linear shape functions, it gives you a C0 function, C0 interpolation. This gives you actually a not even continuous interpolations, like a C minus 1 in the order of continuity. Okay, so this is actually the simpler way how you can interpolate velocities inside your mesh rather than using the piecewise linear shape functions. Because then the idea then you would have some other vertex here, some j, right? You would create analogous. You would do basically the same thing. You would have a barycentric cell for this vertex, right? And there would probably be some other triangle somewhere, so it would have some cell like this. So every vertex would have some barycentric cell with it. Each of the barycentric cells would have the corresponding shape function, and then now I can interpolate my velocities like this, right? Now I can say that my velocities, instead of using the head functions, I can now say that the VP is gonna be the sum. This is the same thing. The velocity samples are also the same, but now I just use the tilde shape functions. Okay. Yep.
So I have a question about the shape of the barycentric cell.
Mm-hmm.
Is it connecting the barycenters directly, or does it go from center to midpoint to center to midpoint?
From barycenter to midpoint to barycenter to midpoint, yes. So it's like you can see it here, right? This is kind of like one piece. This would be like the A piece of the barycentric cell. So yeah, so you go from the, maybe let me show it here. So you first find the edge midpoint, then go to the barycenter, then to another edge midpoint, another barycenter, another edge midpoint, another barycenter, and so on until you get back. This is by the way just one way you can do this. Okay, there are other cells you can devise. There is Voronoi cells are kind of popular, and then there are like some modified Voronoi cells. They come up with like discrete differential geometry. Now, why I'm bringing up these barycentric cells and this like a kind of poor man's interpolation of the velocities is that if you actually do the same derivation we did before, you'll actually see that you get exactly the lump mass matrix directly. Okay, that's kind of the answer to the question I was asking. Like, can you justify the lump mass matrix using finite elements? And the answer is yes, if you define the shape functions like this, corresponding to barycentric cells. Why is that? Well, that's kind of simple, because if you when you are doing the finite element derivation, I will not repeat the whole thing, but you could basically repeat all the derivation we did the last time. And eventually you would get to integrating over one triangle T, so the ET is like a triangle number T, so integrating over the area of one triangle, you would end up having to integrate Si tilde P times Sj tilde P dP, okay? And how much is that? Depending on I and j. There are two cases. Either I is equal j, so I'm integrating the shape function squared, or they are different. And the answer is very simple. So we are on one triangle now. So it's this kind of situation. Okay, let's say that this is triangle T. Let's say that the A is I and these other guys are j or something like this. And I want to know what is the integral of the shape functions over the one triangle.
So if it's the same, because you said the areas are each in 1/3 of the full triangle.
Correct. Yeah,
so
that is
if
correct.
If the same, wouldn't the area of that, if I is equal to j, then it would be 1/3 of the area?
That's exactly right.
If they're different, it would be 2/3.
That's exactly wrong. But you are right on one side. So if I equals j, let me write it like this. For first the answer, then the case when it happens. So it is indeed the area third if I equals j. Because what happens if I equals j? Yeah, somebody said 0, right? That's exactly what happens in the otherwise. Right? Because if I equals j, then I'm squaring this, okay? Well, squaring this does nothing, right? 0 squared is 0, 1 squared is 1, right? So I am basically integrating just the shape function, right? So if I'm integrating over the triangle, for example, the blue one, I get 1/3 of the area. If I'm integrating every other one, I also get 1/3 of the area, okay? So that's why this is always the area of the triangle third. And if I do a dot product of two different shape functions, if the I is different from j, well, then there is no overlap, right? Either one is 0 or another one is 0, but you get 0 everywhere, so it must be 0, okay? Before it, so when we were doing this with the piecewise linear shape functions, this became more complicated because these guys, they actually do overlap, right? They are non-zero. If I look at another tent, another tent would be pitched at this point, so there actually is overlap, and that's why you get these off-diagonal elements I crossed out here. But they actually arise in the piecewise linear shape functions, okay? So this is the answer. This is the finite element interpretation of this mass lumping. And by the way, you don't have to stop here. You can also make things more complicated by going to higher order shape functions. That's called higher order finite elements. You might say that C0 interpolation is not good enough, which sometimes it isn't, right? Last time somebody was asking how does it work in rendering. Like what if you want like nice smooth surface, right? Because on this surface you might see some creases, right? Because there are these sharp edges. If you don't want those, then you can say no problem. You can just use higher order shape functions. So you can use C1 or even C2 continuous shape functions. The problem is, as you can see, it gets much more and more complicated computing these integrals, and also the mass matrix and all the other the mass matrix and all the other matrices for finite elements, they become more and more dense. So it becomes kind of ugly. So some people still like using it, but you kind of pay for it. There is no free lunch. If you want higher order continuity, you can have it with finite elements, but you will pay for it. So on the contrary, you could be arguing, hey, why do we even bother about these tent functions? Can't we just always get away with like the piecewise constant ones? And actually sometimes you can, right? That's a fair question. Now the answer though is that and that's kind of what's going to be the main topic of today's lecture, for discretizing the elastic potential, we will need the derivatives of the shape functions. Okay, we will need to differentiate this. Because unlike the kinetic energy, there are no derivatives in here. The elastic potential, that will depend on some derivatives of the positions. Okay, we'll need to differentiate. Well, and that's kind of a problem, right? Because if this is a piecewise constant, then its derivative is almost everywhere 0. Okay, so that's not very good. On the other hand, if it's piecewise linear, what's a derivative of the piecewise linear function? It's a piecewise constant function, exactly, because if it's piecewise, derivative of a linear function is a constant, right? So it's going to be a constant on every triangle, so altogether a piecewise constant. That's what I mean by piecewise, that on every piece it can be a different linear function or different constant function or different quadratic function or what have you. All right. All right, so that's what we will do in a moment. But before we get there, I wanted to actually correct one mistake I made before regarding the mass matrix. So that's actually the mass in the Hamiltonian form. How do you actually build mass into the Hamiltonian? And previously, I actually made a mistake when I said that you can just take your elastic potential and you can just multiply it by the inverse of the mass matrix. And that's how we can like always assume that the mass matrix is identity, so we don't have to worry about the mass matrix. And I actually made a stupid mistake because you can do this, but the problem is that this is a matrix, okay? This is a 3m, or I said 3n, right, to be consistent. Yeah, 3n. Not that it matters, but just for sake of consistency. So it's 3n by 3n matrix, okay? But this thing is just a scalar, okay? And I don't, it's kind of weird if you upgrade the elastic potential from a scalar to a matrix, okay? I'm not sure how the Hamiltonian stuff would work. Maybe you could make it work somehow, but it's actually not the standard way how it's done, okay? So if you actually want to introduce mass, so this is wrong. if you want to do it right, and that's how it's usually done in analytical mechanics, you actually use the following trick. You replace V with P, which is M times V, okay? And this P, that's called generalized momentum, or sometimes conjugate momentum. It's really nothing but a scaling of the velocities, okay? Because this M is still a 3n by 3n matrix, and the V is still 3n by 1 vector, okay? We assume the M can be anything, by the way, as long as it's symmetric and invertible. So from now on, I don't care, or as far as the Hamiltonian is concerned, I don't care what finite element approximation of the mass matrix I'm using, if it's lumped or non-lumped or higher order or whatever, that doesn't matter. As long as the matrix is symmetric and invertible, I can define these generalized momenta, and that's simply just a multiplication of the velocity vector with this mass matrix, okay? Whatever mass matrix you like. And then what you can do is to write your Hamiltonian. Previously we were writing as x and v. Now you write it as a function of x and p, okay? And it's gonna be still a sum of a potential energy and a kinetic energy. But now the kinetic energy depends on this p, okay? And here is the little trick. The k of p, the kinetic energy of p, is defined as follows: 1/2 of p transpose m inverse and p. That's kind of the trick, the inverse there, okay? Why is the inverse there? It's kind of obvious if you plug in this, because if you do, then you will immediately see this is VT M transpose M inverse M V, okay? So that is equal to 1/2 V transpose M transpose V, but I said that we assume that the mass matrix is symmetric, so this is just VT MV. Okay, so this really is the same kinetic energy we were talking about here, except that the kinetic energy is kind of reparametrized in terms of the p variable. Okay. Oh, by the way, this thing I find a little bit confusing. This is called momenta, but this is not to be confused with the first integrals. Okay, like the linear momentum or angular momentum, because that's the linear momentum and angular momentum. Those are just 3 numbers. Okay, each of them. This has as many numbers as there is degrees of freedom. Okay, so that's a different thing. It's still like velocity times mass is kind of momentum something, but it's not the same thing we were talking about before when we were saying that the motion conserves under certain assumptions the momentum. Okay. And now if you write the Hamilton's equations in this form, so you can write it like this. So you write, so instead of velocities, you basically compute with the p's, okay? So the Hamiltonian equations, they look like this. You still have the gradient of the Hamiltonian at x and p. So basically the velocity is replaced by p. It's kind of like a substitution. That's what you can think about it. So if you don't remember, the j was the 0I minus I0, the 2n dimensional rotation by 90 degrees. And here I have the gradient of the Hamiltonian, right? So if I differentiate by x, I certainly get the gradient of the potential. And here I differentiate the kinetic energy in this form by p, so I get m inverse p. Okay? And if I multiply it out with the J matrix, write it like this, it's clear it's a different thing, then I'll see this is m inverse p, and here I get minus the gradient of the potential. Okay, so if I put it together, this just says that x dot is m inverse p. It's no big deal, it's just a substitution. I just want to convince you that this is really the correct thing to do. Okay, I just like wrote it out. This p dot is this, I put it here. The x dot is this, I put it down here. Okay, and you can kind of see if I do the substitution, you can kind of convert it to the standard equations of motion, right? Because x dot is m inverse. So if p is mv, then I can put mv here. So this means this x dot is v, right? And p dot will be, of course, mv dot, because we assume that the mass matrix is constant. And this is minus the gradient. So I can also write this as v dot equals minus m inverse, the gradient of the potential. Okay, so altogether x dot equals v, so I can write that x double dot equals minus m inverse, yeah, the gradient of the potential, which is really nothing but ma equals f. Okay, that's Newton's second law. So that indeed works. So that's the correct dynamics. Does that make sense? So that's how you can build the mass matrix into the Hamiltonian form. That's what we are talking about. So I wanted to make it easier from the start. So I was saying during the first several lectures that the mass matrix is identity. Okay. When you want to say it's no longer identity, this is how you do it. All right. So let's get to the main topic, and that's finite element discretization or approximation of this potential term of Ex. Okay, as we see, the Hamiltonian is built from these two things, from the potential term and the kinetic energy term. Okay, so we already know how to discretize the kinetic energy term. That's this, right? The VTMV, aka PTM inverse P. That's really the only trig here that you have to plug the inverse in there. So now we have to have a discussion on how to do the same thing for the potential energy. Okay, that's going to be a little bit trickier than the kinetic energy because it's a more complicated energy. So let's first we'll talk about the continuous case. So let's assume again I have some, oops, not this, that I have some domain omega. Again, let's do it in like two dimensions first. And let's say that this domain is deformed by some deformation function f, okay? So in this case, it would be deformed from R2 to R2. It could also be from R3 to R3, right? And this function maps the omega domain into some deformed thing, okay? So this is gonna be some f of omega. This is the image of the set omega under the function f, okay? And like typically you would want some assumptions on the f, right? Like that it's diffeomorphism or something nice, that the function is smooth and so on. I think the only thing we need is that you can compute derivatives. I think you don't even need them to be smooth. So we kind of don't have to make any formal assumptions here. My point is, if I have this kind of setup, so this kind of means that this is my rest pose domain. Okay, so if you are simulating some block of rubber, this would be your rest pose block of rubber. So it would be some box or something, and that will be, now you apply some deformation to it, some arbitrary function that really can change it to anything. And what we want to know is, what is the total potential energy stored in this deformed elastic object? Okay, so if this is like a piece of rubber in some arbitrary shape, that's what the omega represents, then I want to know if I deform it like this, how much energy is going to be stored in the object, okay? So what this really is a fancy generalization of Hooke's law, right? For Hooke's law, basically was the same thing for a spring, right? The spring was that this was like an undeformed spring that was here, maybe like this, right? Like a spring. Then I had the deformation to, let's say I stretched the spring so that the spring was like this, and there was lots of energy stored in the spring, okay? And Hooke's law told me quantitatively how much energy is stored there, okay? So I'm now generalizing to a continuum. But the idea is still the same. I have some deformation, and I want to measure the energy associated with the deformation. That's how you get the elastic potential E. The E, by the way, doesn't have to be just the elastic potential, right? You can also, if you have the Hamiltonian form, you can build there any conservative force. You can build a gravity force in there. We talked about that, right? but that is easy. What we are talking about now is the case of the elastic potential. So exactly these energies corresponding to a deformation of some object. All right, so how do we mathematically do this? So first of all, we need to be able to quantify the amount of deformation, right? Like if it's kind of intuitive. If I stretch this thing like a lot, if some f tilde was like this, then this is like more deformed intuitively, so it should probably have higher potential than something that's less deformed, okay? For example, if I just translate this thing, okay, so if I just do, let's see, if I just did this, so this basically looks the same, and I have some, I don't know, f2, and this would be the f2 of omega, and this didn't deform, only deformed a little bit, but just got translated, then the potential energy should be close to zero, okay? Because there is not much deformation going on. So what I need is a way to quantify the amount of deformation, okay? And in the continuous world, we can do it like this. We can look at every single point here. So as before, I will be integrating over all points in the omega. I call every single one of them of p, okay? I can also say that there are some local coordinates in the material space, some x and y directions, okay? And I can look where this point p got mapped to, okay? So let's say it got mapped to here. That's my f of p. And I can also look where these axes are mapping. Okay, and what I will see is that they are mapping, depending on the distortion, they are now distorted. Okay, and that's the key idea. We want to measure the local deformation around every point P. Okay, and we will integrate this to get the total deformation energy E. Okay, so a question for you: what is the mathematical tool to measure or capture the deformation in a small neighborhood of this point P, in some infinitesimal neighborhood of this point P that gets mapped to some infinitesimal neighborhood here, right? There is some distortion depending on how much you stretch it. If this was just translated, there would be no distortion at all, by the way, right? So what is the mathematical object we need to use here to bring this from to make it concrete?
Tensor, right?
Yep, it's a tensor.
Information matrix.
Yeah, yes, exactly. It's just it's a special kind of matrix is a tensor. We can deal with just a matrix here. Yes, that's right. And we have had this before. It's the very standard concept of linear. So basically the idea is to linearize this function at the point P, where the point P is arbitrary. So the linearization of this function from R2 to R2 or function from R3 to R3, how do we linearize it? By taking the gradient, yeah? or the Jacobian. So that can be written, oops, not like this, that can be written like this. So the Jacobian or gradient, that these things can be used interchangeably. But what's important in this case, that would be a 2 by 2 matrix, okay? Or in 3D, that would be a 3 by 3 matrix. And that's the Jacobian. We write it down. And I understand of f, of function f at point P, okay? Because of course at every other point, the Jacobian can be different, okay? Just to be clear, do you remember what the Jacobian was? Just so we are on the same page. This thing, that's the matrix of the partial derivative. So I take the first component, f1, okay, and I differentiate by all the, instead of saying f1, I'm writing f2. f1, and I differentiate by all the coordinates. f1 by y, f1 by z, okay? Then I do, I'm doing the 3D case already, sorry. Do the 2D one, that's easier to write. Then I take f2 and differentiate by x, and then I take f2 and differentiate by y. Okay, so it's a 2 by 2 matrix. Is everybody clear what is the F1 and F2 meaning here?
You had F2 previously.
And that was a different F2. That was to confuse you. Okay, that's probably a poor choice of notation. I just made that example on a whim, so I didn't think about a notation before. Now the F1 and F2, they are coordinates of this function, right? If this function has two outputs, then the F1, I could write the F as like this, F1 and F2, where F1, 2 would be R2R functions, okay? So this function has, it's like, think about it as a piece of C code, okay? It has two inputs, two outputs. So this means just split one of the outputs and split the outputs. Okay, so the deformation gradient, the Jacobian in this context is typically called the deformation gradient. And that just means that it's a gradient or Jacobian of a function which represents deformation. Okay, that's what you usually hear in continuum mechanics. And once we have this set up, I can tell you what is going to be the potential energy. We can define the potential energy as integral over this domain omega, and it's an integral of some function psi. I'll explain in a second what it is. And the psi is applied to the deformation gradient of P, where P is all of the points I'm integrating over. Okay? And the psi function, that's a function that takes a matrix. So in this case, it would be 2 by 2 matrix. In 3D, it would be, of course, a 3 by 3 matrix. And it assigns it a non-negative number. Okay? And this psi is called energy density function, or deformation energy density function. Let me call it just EDF. All right, so let's think about this formula for a second. What does that mean? So I'm integrating over the entire domain. That makes sense, right? So my P's are basically all points from the rest pose domain, okay? At every point, I compute the deformation gradient, and I feed it through the function psi, okay? It's a density function, so it makes sense to integrate it, kind of like we were integrating density before, okay? But this is a deformation energy density function, okay? So it operates on the deformation gradient, and it tells me how much the material resists to this particular deformation, this local deformation captured by the deformation gradient. Okay, so this deformation gradient kind of measures or captures how deformed this little piece is, and this psi tells me what exactly is going to be the elastic energy corresponding to the deformation for every point, and I integrate this whole thing and get a single number. Single scalar that tells me exactly this potential function, the elastic potential function corresponding to this deformation F. Does that make sense? This is kind of the mathematical way how you can model this. That's really a generalization of Hooke's law to higher dimensional domains. You can kind of see the Hooke's law to be like a one-dimensional version of this. If this was like from R1 to R1, then this is kind of like spring deformations, okay? And even springs can be nonlinear, right? So even the Hooke's law can be generalized even in one dimension. But here we are generalizing to some two, or usually you will be simulating a three-dimensional object, right? Because that's what best models the real world. So this is how you can do it in general. It works both in 2D and 3D.
Question. Sorry, back to the F1 and F2. Are those referring to like the X, Y outputs?
No, the X and Y's, those are my inputs, okay? So in this, and this is, by the way, that's a good question. I should have explained this. This is sometimes called the material space. I'm borrowing terminology from continuum mechanics because that's what this really is. It's material space, and this is the world space, okay? So the idea is that you have this reference configuration of your object. It could be a block of rubber you're analyzing, or or a piece of some biological tissue the biomechanicists are doing, that they take a piece of tissue and then they examine it. If there are no forces acting on it, then you can say this is the material space. This is kind of the natural state of that object. And you can say that I have some coordinate system, okay? That I have some x and y and maybe some origin, if that's what you are, if that's what you want, if that's what helps. So these x and y's, those are the x and y's I meant here. So these f's are differentiated with respect to the material space coordinates, okay? And you're kind of right that in the 1 and 2, that could also be called x and y. But the x and y would be in the world space coordinates, okay? Because I could actually define a different coordinate system if I wanted to, which actually sometimes is not a bad idea. Sometimes people actually write this with like capital letters and capital case or uppercase and lowercase. That's what you can usually see in like continuum mechanics textbooks. And this means coordinates in the world space, okay? And this f is exactly the conversion from the material space coordinates to the world space coordinates. That's the deformation itself. This f thing, that can be changing, right? If your thing is moving, if it keeps deforming, then at every instance of time, this f changes. So actually, it could also depend on time. In practice, it would depend on time. Right now, I'm just saying, let's just freeze one instance in time and look at the deformation itself, regardless of when it happened. Yeah, makes sense? So the 1 and 2, I guess I didn't want to confuse it with these axes, and I think this is a horrible notation because distinguishing upper and lower case is not super easy. So I gave it 1 and 2. So those are like the output components. So the function has 2 inputs and 2 outputs, right? The 2 inputs here are the x and y's, and the outputs are the f1 and f2.
So it converts from local coordinates to world coordinates is one way to say it.
Yeah, that is exactly right. Which, by the way, if you are familiar with graphics, that's how it usually works too. If you load like a 3D model in like a triangle mesh, then it comes in its own coordinates, right? And you typically put it somewhere in the scene where you are rendering it, that you also have some camera and stuff going on, and then you put it in world coordinates. It's kind of the same idea. And it's really just because you have this reference configuration of that object, and then you have some world where it's floating around. So that's why we have these 2 coordinates. But it's easy to get confused about the coordinates, so I didn't even want to bring it up. I just need them to define the deformation gradient, because the deformation gradient, of course, depends on those coordinates, right? If I change these world space coordinates or the material space coordinates, the deformation gradient would change. All right. So let's talk about this psi thing. That's kind of the main thing, right? The Jacobian, that's the standard thing. Integrals also no big deal. Just integrate the whole thing, and we will do it using finite elements. What the psi thing is, so the psi, that's the energy density function, okay? And sometimes it can be split into two sub-functions, okay? I can call them like psi material and psi strain. Okay, that's how people in continuum mechanics usually do this. So the idea is that the first function, the strain, that converts the deformation gradient into some strain tensor, where tensor again means just a matrix. Okay.
Did you put a composition operator between those?
Oh yes, sorry, yeah, okay. That's exactly what I meant. Okay. So that means I can also write it like this. I can also write it like psi mat applied to psi strain of f, good old, or the deformation gradient of f, right? But yes, that's exactly what I meant by this. That's a composition. So meaning first run the psi strain, and then the output of this function becomes the input of this function. The output of this function becomes the value. So it's really splitting the function in 2 pieces, okay? In the first piece, there's a strain measure that converts the deformation gradient into a strain tensor. And then the psi mat, that's a constitutive model or material model. That then tells me how much potential energy this strain represents for a given material. Okay, it's kind of sometimes it's convenient to decouple it like this, because the strain, me write it here. The strain is basically a measure, geometric measure of distortion. It's basically like some processing you do on the deformation gradient, because the deformation gradient is not ideal. I actually kind of just said why when we had the discussion about the coordinates, right? The deformation gradient depends on these coordinate systems, okay? Well, the actual deformation doesn't, okay? Because if I just, or let's talk about the world coordinates, the actual deformation energy should not depend on the choice of the world coordinates, aka or equivalently said, it should not depend on a global rotation of the deformation field, right? Because if I rotate this whole thing, I'm not deforming it, so the energy should stay the same, right? Unfortunately, that's not the case of the deformation gradient. The deformation gradient changes, okay? So that's a bit of a problem, and that's kind of the main reason why these strain tensors were introduced, okay? So the strain tensor kind of distills the geometric amount of distortion from the deformation gradient. And then the material model, that's basically, those are the physical material properties. That says that rubber responds to deformations differently than steel, that responds differently than biological soft tissues, that every material has its own physical properties, and that's what this material part is modeling. Sometimes this is called constitutive material models, but kind of the split is that this is a geometric tool and this is like a physical tool. This is not absolutely necessary, by the way, to do the splitting. That's just a convenience. We can also define the psi directly. I kind of prefer to just do that, to define a reasonable deformation energy function which combines both the material and the way to kind of measure the distortion. By the way, as I'm already introducing all this continuum mechanics jargon, I can tell you that the materials we will be talking about are called hyperelastic. Hyperelastic materials, which basically means that they never break. Okay, that for no matter how big deformation, you can write the energy density function and the potential energy. Okay, you can of course, by finite element models are useful also when you like want to simulate fracture and things like this. But that's an advanced thing. We'll just cover the hyperelastic materials. All right, and to do that, we need to answer two questions. First is how to discretize this using finite elements of Ex. And the second is how to choose or how to define the psi function. So today I would like to talk about this first part. So for now we can assume that we are given this psi. Okay, so assume that some psi from let's do it in 3D now, because that's where you will usually be using it. Let's assume this function is given. Okay, that you have a piece of code which says psi and takes a matrix and spits out a number for any matrix, okay? You have a code for this. And the question is how we are gonna apply finite element discretization to this thing. Okay, that's what I would like to do today. So what we are gonna do is we are gonna use linear finite elements. So we'll use exactly the same thing as before, these guys, okay? These head functions, okay? Except that instead of interpolating the velocities, we are now gonna be interpolating the positions, okay? So I could write, so the xp, so this will be the interpolated positions, and they will be approximated using finite elements using the same piecewise linear shape functions, but I'm interpolating the position values now, okay? So in addition to the v's, also the x's live at the nodes now. Okay, so it should be x3, v3. And I interpolate in the same way I interpolated them here. Okay, and this is kind of nice because why is it nice is because the potential, the continuous potential depends only on the deformation gradient of f. Okay, so if my f, is piecewise, if my f is piecewise linear, then the gradient of f is piecewise constant. Right? Because the derivative, the Jacobian of a linear function is a constant function. Okay. So that's nice because that means the Jacobian of f will be constant on every triangle or tetrahedron. Okay, let's just talk about tetrahedra from now on. Let's do the 3D version. The 2D version would be the same just on triangles, but usually we'll be doing this in 3D. So that is nice because that kind of brings us to the discontinuous, the easy case, which is easy to integrate. Because then the integral over the entire domain will essentially be summing the contributions of the individual tetrahedrons. Okay. The only question now is how to actually compute this deformation gradient with the linear finite elements. And that is usually denoted as capital F. Okay, it's still a 3x3 matrix, but now with the assumption of linear finite elements, it's a constant on every tetrahedron. And we need to compute the matrix corresponding to the deformation of the tetrahedron. So just to give you an idea of what we are talking about graphically, I prepared this image. Here. So basically you can imagine that we now did the usual thing. So we chop this into finite elements. Okay, so tetrahedrons if you are in 3D, triangles if you are in 2D. And all of these guys, they get distorted somehow, right, by the deformation F. They get more distorted, more or less distorted depending on how the F looks like, okay? So we are going to look at a single tetrahedron here, okay? So let me call the material space coordinates of the vertices of the tetrahedron. Those are the vertices of the tetrahedron. Let me call this x1 hat. This guy would be x2 hat. This would be x3 hat. And this would be x4 hat. And this is my mapping F. And the tetrahedron gets deformed into coordinates x1, x2, x3, and x4. Okay, so this is the material space or rest pose. This is the world space. Okay, the F is still the mapping from the material space to the world space. Now, since F was linear, or I guess technically affine on every tetrahedron, then the tetrahedron gets a map to another tetrahedron. That's the beauty of linear finite elements. Okay, if you are doing higher order finite element, no longer the case, things become a little bit more complicated. Okay. All right, so how do we compute the deformation gradient? This F, which is nothing but the Jacobian of F, which is constant on the entire tetrahedron. Okay. Well, since the function is linear on the tetrahedron, then the mapping from, then I can write it like this, right? Fx tilde plus b, where this is a 3x3 matrix, and this is just a 3x1 vector. Okay, this x tilde, of course, is okay. Let's just stick with the 3D case for now. All right, this is kind of boring. This is just saying x3 is f x3 tilde plus b, and x4 is f x4 tilde plus b. Okay, this is just saying that the same mapping is applied to all of the nodes. Now the trick I can do here is I can subtract this last equation from all the previous equations. Okay, so if I subtract it from the first one, I will get x1 minus x4 equals f of x1 tilde minus x4 tilde. Okay, and the beauty of this is that the b disappears. Okay, this offset kind of term. Then for the second minus the fourth equation, I'll get this. So f x2 tilde minus x4 tilde. And then x3 minus x4 is nothing but f times x3 tilde minus x4 tilde. Okay? I took all of these equations and subtracted the last one from all of them. That made this b go away, which is kind of exactly what I want because I want to isolate exactly this f. Okay? Which, by the way, exactly corresponds to what I said before, is that the translation of the entire object should have no effect on the amount of potential energy. Okay, which is exactly what we are getting here. So this thing we can write in a matrix form. We write it in a matrix form. We just stack these vectors. All these guys are 3x1 vectors, right? So I can put them as columns of a matrix. x2 minus x4 and x3 minus x4. Okay. And I can call this matrix ds. It's a 3x3 matrix. Okay. Then the right hand side, so this f, that's also a 3x3 matrix, right? Or write it properly. R 3x3. And here I have the same thing with the tilde. So x1 tilde minus x4 tilde, x2 tilde minus x4 tilde, and x3 tilde minus x4 tilde. What are these things, by the way? The x1 minus x4 and with the tildes. Those are just the vectors corresponding to the edges. Okay, if I was to draw it, then the x1 minus x4, that would be this edge, right? The x2 minus x4 would be this edge. Let me use a different color to make it super nice. R would be this edge. That would be the x2 minus x4 tilde, right? And there would be the x3 minus x4 tilde, that would be this last edge, okay? And then, of course, I have the same edges also in the deformed tetrahedron, right? So the x1 minus x4 is this one, and so on, right? So here, those are the matrices of the edges. I can also name this matrix. I will call this dm. I think the m is for material. I did not invent this notation. I took it from the tutorial, which is, by the way, a very good tutorial, which you can look up, www.femdefo.org. It's a very nice SIGGRAPH course by Eftichios Sifakis and Yerney Barbich, where you can find more details about all this stuff. And I'm reusing their notations. So if you are reading this, this all looks familiar.
So that's femdefo.org?
Yep.
Okay.
It was a SIGGRAPH 2012 course for like finite elements applied to physics-based animation, so for graphics people. Which the linear FEM, that's basically what everybody's using because it's so convenient. Yeah, so this this equation is ds equals f dm, right? All of them are 3x3 matrices. So if I can invert the dm, which I should be able to, then f equals ds dm inverse, okay? Where the dm depends only on the respose, okay? All these tildes are the respose. So if the respose is not changing, which is usually the case, usually only the world space coordinates are changing, only these x's are changing, the x tildes are not, okay? Then this dm inverse, that can be pre-computed, okay? And only this ds kind of depends on the state vector x. That is definitely changing because your thing is moving, right? Ultimately, we are also still simulating motion. But what you can do, you can pre-compute these matrices that depend on the respose. By the way, what about the inversion? Will it always, why am I so confident that you can always invert it? Any ideas? What would it mean that you cannot invert the material space tetrahedron and the, I guess, edge matrix of the tetrahedron, right? Because that's what it really is. Well, if you couldn't invert it, that means that the tetrahedron has volume 0 in the rest pose. That means that it's degenerate. And that means you have a bad Tet mesh, okay? Even if it's not 0, but already, no, not singular, but close to singular, then you already have a bad Tet mesh, okay? You need to run your Tet gen or whatever you're using again, because that's not gonna simulate very well. The finite elements should not be degenerate. Okay, so this is how to compute the deformation gradient. And that's kind of the hardest part because the rest is kind of simple. If you want to, the rest, meaning the rest of applying the finite element discretization to the elastic potential. The elastic potential is this, okay, so let me write it again here. The elastic potential is the integral over my domain of the energy density function of the deformation gradient of arbitrary point inside the domain, okay? Well, now using, and now I will apply the finite element approximation, okay, using the piecewise linear shape functions, as we said. So that splits into a sum over all tetrahedrons, okay, T. For every tetrahedron, I integrate over the tetrahedron, so that's the ET, similar to what we had before. This psi T means that's the energy density function for tetrahedron number T, okay. So that's, finish this first. So the psi T, that's the energy density function for tetrahedron number T. And I just put the index there so that every tetrahedron can have its own material, okay. It's a similar kind of idea like why we had the different densities for every tetrahedron, because potentially there can be some object like the human body where the bones behave very differently than muscles, for example. And of course, the deformation gradient is also going to be different from every tetrahedron, right? Here I just assume pick one tetrahedron. Here is how you compute the deformation gradient for it. Of course, for a different tetrahedron, you get a different F, so that's why the index T here, okay? Now, the beauty of this linear finite element discretization is that this deformation gradient is constant on the entire tetrahedron, okay? So this thing you can exactly evaluate using like 1-point quadrature, if you will. If this is constant, but that's already like trying to be too fancy, I guess. This is because this is constant, then this is nothing but the value times the volume. Okay, let me call the volume WT to be consistent with the notation. So this that is that. Okay, where this WT is the 1/6 of the determinant of dm. That means the volume of rest pose that ET. Okay, everybody knows that's how you compute the volume of a tetrahedron, that you take exactly this edge matrix, you compute the determinant of it, you take absolute value just in case that happened to be negative, which it shouldn't if you have your elements oriented nicely, but just to be on the safer side, you take the absolute value, divide by 6 because you did the volume of the parallelogram, similar to the area of a triangle, except that in 3D, okay? And this is because this value was constant, so this is just that constant value times the volume of that element. And that's basically it, okay? Now you know how to compute the finite element discretization of an elastic potential defined like this with linear finite elements. Okay, so what you can do for every tetrahedron, you compute this ft. Okay, this is how you compute it. Okay, you know exactly what coordinates the tetrahedron has because that's your current state of the simulation. You also know the coordinates it has in the rest pose because that's where it started. So you can compute this f for every tetrahedron. I told you we assume that you have the code for the energy density function. Typically, by the way, this would be the same for all the elements. Typically, you would assume homogeneous material, that the material is exactly the same everywhere. Okay, so then you could drop this index t, then this would be just a constant psi function. Or if it's different, you typically just vary some parameters of this of the psi function. That's what we'll talk about next time. How do you actually define nice psi functions? And then you just multiply by the rest post volumes and sum it together, and you're done. By done, I mean you have a finite element approximation of the elastic potential function. All right, so I can give you one more thing to think about for the next time. There is one funny thing about the deformation gradient. So the deformation gradient, so if I assume that the rest post is constant, okay, let's assume this thing is not changing, but this thing is changing. Okay, so this dm is really constant during the course of the entire simulation, but this ds, that depends on x, and the x is changing. Okay, so that means that the deformation gradient is a function of x. Okay, now it needs to be a linear function of x, right? Because here I'm just subtracting, that's a linear operation. Here I'm doing matrix multiplication with a constant matrix, that's also a linear operation. So this f needs to be a linear function in f. Okay, sorry, I meant linear in x. Okay, so that means that I should be able to write f as using some matrix, g times x. Okay, this is not true. Technically, this would be actually a tensor. Okay, this would be like a proper tensor, because what we really want is, so this x, the x is 3n by 1 vector, right? Just like the velocities before. So this g actually should be something that converts this 3n into a 3 by 3 matrix, okay? 3 by 3 matrix, okay? So if you have a mapping from a vector to a matrix, that's gonna be a tensor, okay? Now there is, fortunately, a convenient way to fold this tensor back into a matrix, okay? So we don't have to be like writing new like functions to deal with tensors. And the question for you is how this G operator actually looks like once you unfold it into a matrix. Or even how to actually wrap your head around this. The fact that this, if I have linear mapping from a vector to a matrix, how to fold it and how to represent it using a matrix so I don't have to go to a tensor. I'll explain that on Thursday, and we'll also talk about how we'll start talking about the material models, how to actually define the psi. It's kind of fun. All right, any questions? If not, I'll stop here.